Welcome back to lecture 22.1, where we're talking about the squeezer. Okay, so just to recap, last time in 21.1, we talked about thermodynamic potentials and Maxwell relations. And in 21.2, we talked about the thermodynamic square. Following that, we used that thermodynamic square in our Maxwell relations in class for an example, which was the squeezer. So I want to continue on with the squeezer here in 22.1, and we're going to talk, I'm going to start by recapping what we did in class, okay? So remember in class, the example was to isothermally compress 1 liter of mercury from 1 to 470 atmospheres at 30 degrees C. All right, so when we were doing this, we wanted to find the work and the heat. If you look back at lectures 5 and 6, we had already done the work in that class, right? And to do that, we needed our three-dimensional equation of state. Remember, our three-dimensional equation of state was dV, was beta V dt, minus kappa V dP. And so our work, dW, was minus PdV, right? So that's minus P beta V dt plus kappa V dP. And so what we did was we put in our work. We did this integral. So for isothermal process, this was 0. We did the integral, and our work was 1/2 kappa V P. Oh, nope. Oh, why was... Oh, yeah, I missed the P here. Plus P kappa V dP. There you go. Evaluated. Okay, so what we got was positive 43 joules. So this is now the third time you've seen that, lecture 5, last class in class. But the trick from last time, or the thing that was new, was that we had calculated dq, right? And how did we do that? Well, we knew we could calculate dq if we found ds. And so we asked, what is ds? So we said, what if s is a function of p and t, right? So s is a function of p and t. And so we can write our differential, our exact differential, because it's s is an equation of state. All right, and what we did was we wrote out this differential, and then we had 2 terms, partial s, partial p, constant t, dp, and the second term, which was proportional to dt, but dt was 0 because this was an isothermal process. And delta S, delta P, or partial S, partial P, and constant T was not really something that we could connect to physical reality. So instead what we did was we connected this with a Maxwell relation, right? And so this is a good example of how you need these Maxwell relations, why these Maxwell relations are so important, because they allow you to do this problem, right? Asking the heat in this problem. And so the one we found was minus partial V, partial T at constant P. BP. And using that, that was just a reminder that our coefficient of thermal expansion, beta, was 1 over V, partial T at constant P. So our ds was equal to minus beta V dP, and dq was minus T beta V dP. Or Q was minus T beta Vp, evaluated from P1 to P2. Okay, so we put in our numbers for mercury. 1.8 times 10 to the beta was 1.8 times 10 to the minus 4 inverse Kelvin, and we got minus 2,584 joules. 2,584 joules. That's right. All right, so a couple of points was this was negative. And so since it's negative, that means that heat is flowing out of the system, right? Negative heat flows out. Heat is ejected from our system. Okay, so this is pretty interesting because if you imagine this as a heat pump, right? So you have our heat pump, TC, TH. If you put in some work, the heat is flowing and so we actually are going to eject from a cold reservoir into the hot reservoir 2,584 joules. That's quite impressive. And if we looked at that in terms of an efficiency, let's call it the squeezer efficiency. Eta HP squeeze. We got 2584 over 43, which is like 60. So that's the most efficient heat pump we've seen. It was more efficient than freezing ice, which we had a 12.4 for our efficiency. Okay, so why is this such an efficient heat pump, right? Could we use this, for example, to take heat out of a cold environment and heat our houses with, right? Heat CSIS, for example. Heat wherever you're hunkered down. So, yes, for sure you could, right? Now, again, like the ice problem, you might have to be moving ice outside. Here, you might have to be circulating mercury. Okay, so mercury is really nasty. It's expensive. It's toxic, right? So we don't want to use mercury. Okay, so could we imagine using something else? So this is such a great refrigerator. Could we use something besides mercury? So, best guess we should always try to do is we should always imagine, could we use an ideal gas? Okay? Could we use an ideal gas to do this? Some of you may already know the answer because what you should think about is that if we go back to our first law, du is dq plus dw, our internal energy is changing. This is minus 2,584 plus 43, right? Minus 2,541. The squeezer is efficient because we had a large change in the internal energy, right? The squeezer is basically pulling heat from the internal energy of the mercury to use it as a heat pump. Okay, so already you know that an ideal gas's internal energy is proportional to the temperature, right? You should know, remember, for an ideal gas, the internal energy was N C.B.T. So if delta T was 0, then delta U should be 0. Okay, so to prove this, right, to do this more generally, let's prove that an ideal gas can't act as a squeezer by proving that delta U, delta V, sorry, partial U, partial V, at constant T is equal to 0. That is, if we hold the temperature constant and we only change the volume, squeezing it, there's no change in the internal energy. If we can prove that for an ideal gas, then we can prove that an ideal gas doesn't work as a squeezer while mercury does. All right, so this is a nice example. So to do this, let's imagine starting with our central equation. You can see that's a nice starting point because we already have partial U and partial V. Okay, so let's write it now. Let's divide our partial V, our partial U through, our partial V through, I mean, is T ds dV minus P. Or really, we should write partial U, partial V, constant T, equals T, partial S, partial V, constant T minus P. Okay, so when we look at that, we start to imagine already the problem we're going to come up with, right? The problem is connecting this change in entropy when you change the volume to physical reality. This is kind of similar to what we saw last time. So let's change this with a Maxwell relation. All right, so let's draw our thermodynamic square again. So we've got our let's see, S and V over here, which is our extrinsic, and we're going to go alphabetical from bottom to top. We're going to have P and T over here. We're going to have F, G, H, and U, and we have our arrows. Okay, so we have partial S, partial V, partial T, so that was 1, 2, 3. And so we get partial S, partial V at constant T is equal to, so we need the 1, 2, 3 the other way. 1, 2, 3. We're going to get partial P, partial T at constant V. Great. So this says partial u, partial v, constant t. By the way, that was plus because we were symmetric around our arrows. Equals t, partial p, partial t, constant v, minus p. So far this is totally general. And this is actually called the first energy equation. But now let's do it for an ideal gas. And explore what partial p, partial t, constant v equals, right? So how are we going to do that? Well, we need our equation of state. PV equals nRT. Aha! Partial p, partial t, constant v is simply nR over v. But remember, nR over v is the same thing as p over t. So we can write partial u, partial v at constant t equals t times p over t minus p. And you can see we get 0. And so we have proved that an ideal gas cannot operate as a squeezer heat pump. Such a good idea, though, to use a squeezer. Maybe we should use something else. What do we have that isn't an ideal gas, isn't toxic, but is instead abundant? Okay, so imagine using an abundant liquid, since we know a gas won't work, and squeezing it. And liquid's nice because we can, bring this liquid in, we could exchange it with our environment. How about we use the water in the North Saskatchewan, how do I spell Saskatchewan? Where's my eraser? Saskatchewan River. Okay, so we're going to do this in winter where the water is about 0 degrees C. Okay? So let's use this as our medium for our squeezer. We're going to squeeze it and see how much heat we can extract. Okay, so let's a couple numbers we're going to need. We know that we're going to need kappa. So that's going to be 5.09 times 10 to the minus 10. Make sure I get meters squared per Newton. And we're going to need beta, and that is minus 6.79 times 10 to the minus 5 inverse Kelvin. Maybe we should do this as an example in class. Let's do this as an example in class. And we'll see what we get, okay? So we'll end 22.1 there, and then we'll move on and do another example using our Maxwell relation next.